Hey, welcome back to physics. This video should be number 2 in the circular motion series. At this point in time, you should have already either attended the original board meeting or watched that introduction video. This one we touched on, it's worth covering. An object is going in a circle, and then that force that's causing it to go in a circle stops. So if you recall, something going in a circle has to have a net force directed toward the center. In this case, I've got an elaborate pea shooter. If somebody shoots this pea through this track, when it shoots out here, I want to know what the pea will do once it is out of this pea shooter. Will it keep going in this circle? Will it go in this direction? Will it go off on the one labeled as C? Will it go out but kind of curve? Or will it go just straight out? To be clear, I have had students that have answered all of these with strong arguments and strong beliefs on any of these. Only one of them is correct. Pause the video now and answer this for yourself. Okay. Well, here's the thought process that I hope that you had. As soon as it's out of the pea shooter, it no longer has that force, that net force pushing it toward the center. At this point, it becomes balanced forces. So it should start doing whatever it was doing and keep doing that. That's that inertia concept. It should go in a straight line, the same direction that it was moving at the moment that the net force was eliminated. If you follow that path, when the P gets to here, it's moving that direction. It is moving perpendicular to the radius or tangent. It's moving in a tangent. The path is a tangent to the circle. Tangentially. You try that one for yourself. See if you can get it. It's moving at a tangent to the circle. So B would be our correct answer. And it's interesting. I'm going to go off on a tangent here for a moment. Meaning, instead of to continue on the path that we have intended, I'm going to take a straight line and just keep on going with that. And, oh my goodness, that's where the phrase off on a tangent actually comes from. So for circular motion, to quickly review the 3 things that we know now, if something is going through uniform circular motion, so going at a constant speed but in a circle or through part of a circle, the velocity is at a tangent to the circle. The force is directed toward the center, the net force, and the acceleration is also directed toward the center. That's the one that makes the most sense because the acceleration and the net force are going to match each other. The net force, when we have something going in a circle, happens to have a special name. We call it a centripetal force. Some of the videos out there will have people label a centripetal force. Have we ever labeled the net force on the force diagram? No. Should you ever label a centripetal force on a force diagram? No. Centripetal is just the name for a net force when something happens to be going in a circle. Cool little thing that I saw. I figure I'll throw this one at us as well right now. I've got 3 different situations. In each case, I'm going to say the thing is moving this way. If I have a net force that is moving the same direction same direction as the motion. Well, notice the acceleration and the net force are always the same. If that net force and acceleration are the same as the direction of motion, then the result will be, you tell me, I'll write it down, see if you know it. That's right, the object is going to speed up. If, on the other hand, you have the net force and therefore acceleration opposite the direction of motion, what will happen to the particle? Again, you think it through while I write it down. Hopefully you said that it would slow down. Awesome. So this last one is the one that's kind of really weird. You have something moving this way, and that net force is directed perpendicular, and the acceleration is perpendicular to the motion. Then you end up with a change in direction, or something that is going through a turn. Again, I want to emphasize it may be going in a circle, but it does not need to be a complete circle. It can be through just part of a turn. Think driving. You don't often drive in circles, but you often go through curves, which is part of a circle. Next up. One of my favorite toys right here. It is called the spill knot. I have some water in this. I put some food coloring in it so it's a little bit easier to see. And you may be worried, heck, you may be thinking that I'm lying here, but no, it's definitely a liquid. But when I have it on this thing and walk around with it, it's not going to spill. Let me do a couple out here. Whee! I can move it around like this. I can even do that. Oh, you were scared, weren't you? It's not going to spill because it is a spill knot. And in fact, if you can see this, whee! I don't know if you can slow that down, but that liquid surface is always staying pretty darn close to perpendicular. That's awesome. Well, why does this happen? Well, whenever I'm applying a net force to this, since it's coming from here, which is the center of a circle, that means the net force is always directed this way. The motion is going to be perpendicular to that. If the net force is always this way, why would it spill? I was so proud last year. I don't want to stir up any bad feelings here, but last year we had done this, and shortly after that the senior music trip happened. And I had a student that came back who had a somewhat open container of some hot beverage that wasn't tea, and was worried about it spilling. She came up with a brilliant idea. She had something where she had it strapped, hanging by a string from the seat in front of her, and it worked beautifully. It never spilled. Awesome. Physics at work. Or on a bus. Gonna try and do this one more time. Hopefully I can do this in slow motion. Well, I won't be in slow motion. I'll slow the video down. Hopefully I can get this with enough light that you can see this. Here goes nothing. Okay, moving on to our next setup. It would be nice if we had some equations. We'd like to develop some equations here. Turns out there's a couple different ways that we can calculate A sub c, or centripetal acceleration. For one, I'd like you to kind of think about driving a car through some turns. What situations with driving would cause you to feel a larger acceleration? Remember, the larger the acceleration, the more you're going to feel like you're being thrown to the outside of the turn, even though we know that means you're accelerating toward the inside of the turn. Okay, how about you over there? That's absolutely right. The faster you're going, the more you're going to feel it. So that sounds to me like it's a direct relationship. So that would probably be up on top. Please note this is speed, not velocity. What else? What else might have an effect on how strong that feeling is of being thrown out, or what else would have an effect on the acceleration you are experiencing? Yep, go ahead. Awesome. So you're suggesting that the radius has an effect. So let me ask you this. Does a larger radius, so a bigger curve, a bigger circle that you're driving through, would that result in a larger acceleration or a smaller? Another way to put this is this a direct relationship or an inverse relationship? Well, I think if you're going at the same speed, a tight corner, you feel thrown out a whole lot more. That's why we slow down when we go through those. So that would suggest it's inverse, which means it would have to be on the bottom. Now, when you check the units on this, though, that's not working out. Something isn't quite right. These really are the only two variables. What could we do to make this equation work and have our units be the meters squared for every, meters for every second, or meters for every square second? Still don't know what a square second is. What could we do? If, while I was erasing, you suggested, hey, let's square that velocity and see what happens. Why, by Jove, that works. So our first equation is centripetal acceleration can be calculated by taking the speed squared and dividing it by the radius of curvature. That's our first equation. The second equation relies on how fast, relies on period. So I'm going to take us back. In class we do this in a little bit different order, but if something's going around in a circle, how could you get an equation for just how fast that object is going? Well, we'd want to know how far it has to travel. How far does something have to travel if it goes around a circle once? You darn well better know that that's 2 pi r. So speed is our distance over the elapsed time it takes. Distance going around in a circle is 2 pi r. The amount of time it takes. Do you remember what the time it takes to make one full revolution or rotation or cycle is called? If you remember that that's called the period with a capital T, the symbol, not the spelling, you win the prize. So the speed of an object going in a circle can be represented by 2 pi r over t. R is the radius of the curve, t is the period, the time it takes for one full revolution. If you take this and plop it into this equation, go ahead and do that for yourself right now. Seriously, do it and simplify it down I'll let you work on that while I fill it in on the board, so I won't even bother pausing this. There you go. Our second equation is 4 pi squared r over t squared. T mean, again, the period, the time it takes for one full revolution. So you're saying, you may be saying, why do we have two different equations? Well, this one is great when we're talking about cars or when we know how fast something is going. Cars, roller coasters, this one works great. This one is handy when it's something where we know the period, the time it takes to go through one full circle. So say, for example, you have a bucket half filled with frozen peas and you're swinging that around your head. You might ask, why are you swinging a bucket full or half full of frozen peas around your head? Because you believe in world peas. This equation works great for that type of a situation. Did you expect anything else? Seriously? So those are our two equations. I will have a number of a number of links posted so that you can be getting some other sources here. One or two of the links are going to be of some very stupid people. Don't try them at home. Don't try them at home. I show bits of those in class because it's amazing how stupid people are. You're going to see people on a playground merry-go-round and somebody makes the thing spin really, really fast. It looks very dangerous because it is very dangerous. The people themselves probably think they're being thrown out. But remember, if you can see it, I pick a couple of them where you can actually see that once they lose grip, they go off on a tangent. Stupid. Don't try that at home. I've also got one that uses I've got a couple dealing with my spill knot, and in fact one person that has a quadcopter that does the same types of things as the spill knot. Very cool. I'll also be sending out the first worksheet. Just do problem 1 for now. If If you want to try and work on the rest, go for it, but problem 1 will be the next video or answer sheet that I provide. Have a great weekend, y'all. Keep physicsing. Take care.